We will record. You hate Google Classroom? I'm sorry.
Update of it. They
Oh.
updated it, and now it's all fancy, and I don't like it.
I'm sorry. And we will do one chapter of motion in one dimension, and then we'll go to 2 dimensions. We will not do 3-dimensional motion here because your heads will explode and your eyes will bleed and your souls will tear. I don't want to do 3-dimensional motion. Neither do you. If you're going on to engineering, you'll do it anyway. You are doing 3-dimensional motion all the time. The question I have for you is this. My favorite object in the whole world. My coffee cup. Is it moving?
Relative to what?
Ah, there you go. So is it moving? Well, relative to the desk, is it moving? No. Relative to the floor, is it moving?
No.
Relative to the ground underneath the school? No. All of those, no. Relative to the sun?
Yes. Yeah.
Yes. So we do always look at frame of reference for motion. And this is where we know that motion occurs in 3 dimensions that we are capable of perceiving. As I've said, and I think I misspelled perceived, didn't I? It always looks wrong to me no matter how I spell it. Eyes and E's. Blah. The physics seems to posit that there are 11 dimensions, but some of them appear to be curled up inside of one another, so who knows? It's all weird. The axes that we use are the X, the Y, and the Z. X and Y are the ones that you're most familiar with. The X, the Y, the Z. And if you suffered through chemistry with me and you talked about orbitals, you'll remember the dance, the X, the Y, the Z, or the Z coming at ya. Because the Z-axis is the one that comes out into space. That's easy. Okay, when we're talking about one-dimensional motion, we are dealing with one dimension. Duh. We're going to start off dealing with only the x-axis. And we will talk a little bit about displacement. So displacement is your difference in initial and final position. And this is where that delta comes in. So delta x is the difference in your initial x, your final x position and your initial x position. So if this is a railroad track or a number line or whatever it is, if this is 0, 1, 2, 3, 4, 5, 6, 10, if I start at x equals 1, I don't know what my units are here. They could be, ducks, dirty socks, M&Ms, no idea. And I end at x equals 8. We'll say these are meters. What's my displacement? 7 meters. Easy. Final. This is my final x position. This is my initial x position. A note about subscripts. We use them a lot in physics. They're pretty important in terms of keeping track of things like initial and final. Pretty soon we'll be using them to keep track of things like x-axis versus y-axis. That's in Chapter 3. So you want to get used to using appropriate variables. What if my initial position was 10 meters and my final position was 5 meters? Now what's my displacement? -5. So you can have a negative displacement. It essentially means you're going backwards on a number line. If we think of that one-dimensional motion as sort of a number line. Now, let's make something clear. That's you getting out of bed. It's you getting out of bed in the morning. How many of you woke up in your bed this morning? Not on the couch, not in the recliner in the living room, not on the floor in the basement. I don't want to know. Okay. If you woke up in your bed this morning, the question I have for you is, did you wake up in the same spot yesterday? Well, in the same bed. Okay, you woke up in the same bed yesterday as you did today. We're going to assume that you didn't stay sitting there the entire day. So you may have started your day and gotten into the car, and then you may have gone to Tim Hortons, and then perhaps you went to school, and then you went over to the track, and then you went to your friend's house to pick something up, and then you came back, and then, oh, let's see, you went back to the track because you realized you forgot something there, and then you went back, but you went the other way, and you went to Calcutta, and you went to Big Lots, and then you went back to Tim Hortons because what the heck, they have those 2 for sandwiches, and they're amazing. And then you went to work for a little while, and then you went back and got out of your car, and you got back, and you went to bed, and sunset. Well, presumably the sunset before you went to bed. And you woke up the next morning. You sure went a lot of places. This is the distance you traveled. Now, what's the change in your initial and final position? Don't yell it out. Tell one another. You got nowhere, people. Just remember that every single day. You get up and you go a whole bunch of places. You didn't get anywhere. If you end up back where you started, yeah, isn't that like disheartening? And I'm sorry, but the way to frame this philosophically is that even though you appear to be making no progress, many things are being learned and encountered. So, okay, but in a physics sense, really, you got nowhere because your delta x equals 0. Doesn't matter how many kilometers you traveled. Doesn't matter how many meters you walked. Delta x is 0. This is why I like backpacking on loop trails, because I can always say, well, yeah, I saw a whole lot of stuff, but I really got nowhere. So I'm getting right back in my car at the end of the trip. Displacement and distance are not the same thing. So distance is an absolute value. We cannot take the meters. We can't roll back the odometer on your car. We can't roll back the odometer on your sneakers. Distance is just absolute. There's no direction to it. Displacement, on the other hand, has a direction, and we very often, most often, use sign as a proxy for that direction. And we kind of hinted at that in this slide. That here, delta x equals -5 meters. So displacement, we have to be really careful with sign because it does depend on the difference in x and y position. Not x and y position, x final, x initial. Sorry. So now we get to the first of the variables that we're going to use, and that's velocity. So we have to be really careful with the words speed and velocity. Velocity is rate of motion. It's how much time it takes you to change your position. And we typically, so we use a couple different velocities, but average velocity is a really useful one because average velocity is literally just your change in position over your change in time. So delta x over delta t equals v sub a, v average. I'm going to give you a note card. So your little note card is going to end up with a bunch of formulas on it. You're going to use that note card when you're doing homework, when you're taking quizzes, when you're doing anything. Or if you choose, you could just get it tattooed on your forearm, which would be very convenient. And a note card sized tattoo, I think, would look great. So the very first, I'm mostly kidding. I've talked about it. The very first thing that you probably want to write on that note card is that V average equals delta x over delta t. I used to not write that one on the note card, and I used to tell people, you don't need to write that one. You'll remember it. No, you won't. Because if you don't have it written, it's the simplest one. But people, when they panic, forget the simple pieces. So it's good to have the simple pieces written there. So that is the very first thing. Now, your change in position, if you remember, is just equal to your final x position minus your initial x position. That's your delta x. And by the same token, we talk about delta t, change in time. That's from, t equals 1 second to t equals 5 seconds. Well, then delta t equals 4 seconds. We're used to thinking about time as just, it's at the 5-second mark, and we're used to starting at 0. But remember, you can start measuring from some point other than 0. So, t final minus t initial. So that's also equal to average velocity. And we're going to use that and manipulate it to get a whole bunch of other equations, which will be lots of fun. This is the distinction between velocity and speed. Speed is just distance over time. Velocity is distance over time plus a direction. Where are we going? So 10 meters per second west is a velocity. We'll talk more about vector quantities in the next chapter, but that makes it a vector quantity. Things that are given as pure magnitude are scalars. So distance traveled is always scalar. Velocity is always a vector. That's all that you need to know to do the first set of problems. So, page 44, we will do the sample problem together, and then the 2A practice problems are all assigned.